I'm going to be talking to you about a slightly different topic today. This is about something that is not current and present today, but is coming very, very soon. A lot of people are working in this area, and it's going to be quite important in the near future. I'm going to go as quickly as I can through this material because I realize for most of you, I'm standing in between you and evening cocktails. So I'll go as quickly as possible, but hopefully still have some good questions here at the end. Really quickly about me, I am not a safety expert by trade, but I work with a lot who do, and I've learned a lot through this process. Um, what I'm sharing with you today is the culmination of kind of many years of experience and research and thought put into a process. This is not my kind of own original work, but I'm the one who is fortunate enough to be able to share with you today. Everything I'm talking to you about, I tend to use automotive terminology because that is where I live day to day, but a lot of these concepts, they apply equally in other domains, industrial, robotics, medical, things like that. Okay. If you remember nothing else from this today, I want you to remember just a few key things. Safety, unlike other domains, has a level of difficulty to it that I haven't experienced elsewhere. I've worked in hard real-time systems. I worked in high availability systems. I've worked in mass market systems with billions of devices in production. Safety is a different beast. There's also not a single definition of safety, like you might have in some other examples. Safety it varies by industry, it varies by customer, it varies by manufacturer, by product. It's highly contextual. So what is safety for one particular product might not be safe at all, even though the software and hardware could be common. There's a lot of commonality with security and security mechanisms, but there's a difference in direction. Security attacks from external malicious actors. Safety, you tend to want to prevent internal actions. You prevent the system. You prevent bad actions from within the system, not from without. And there's a fundamental scalability problem that I'm going to be talking to you about with Linux today. It's easy enough to qualify a very small subsection of code at the function level. Doing it for entire systems is another story. Okay, what is functional safety? Why is it challenging our approach, and how are we going to use it? If you can remember two things about the presentation today, this is the other thing I recommend everybody know. It's the simplest expression of functional safety that I've seen. This comes directly from the standard. But functional safety itself is the absence of unreasonable risk due to malfunctioning systems. That's kind of what it all kind of boils down to. This is, again, the automotive ISO standard. So as engineers, you may be wondering, all right, how do you measure risk? How do you determine whether it's reasonable or unreasonable? And that's a big part of what safety process is about. Malfunctioning behavior in these systems, hardware and software engineers call these bugs. So how do you prevent bugs in these systems from interfering with your safety goals? Okay, fortunately, we have various industry regulations to guide us. Most of my work has been focused in the automotive domain, ISO 26262, but there's another kind of parent standard, IEC 61508, that a lot of things are kind of derived from. So there's kind of a lot of overlap in standards. So what I tend to see is things that are automotive specific are in this one domain, but anything else beyond that, you'll tend to see according to a general standard, which is then easier to adopt to domain specific standards. We also get requirements from the laws of physics. So this is a completely contrived example, but imagine a safety requirement where you had to perceive something and react within 1 meter of movement. Now, if you're driving this car down the motorway here in London at 100 kilometers per hour, that 1 meter of movement gives you about 36 milliseconds to do something. So your safety requirement then is kind of bounded by time. So you can imagine that time you might have to take in various forms of sensor input, radars, lidars, cameras, ultrasonics, whatever they may be. You may have to do object detection. You may have to do motion inference. You might have multiple pipelines set up to do this because this is a safety-related system. Then you have to take reasoning, make some decisions about what you're seeing. And then from those decisions, then you might have to take actions as well, do some actuation. You might have to do a braking maneuver or a steering maneuver or a chime or something. So you can imagine rather large pipelines, rather compute-intensive pipelines start building up and have to be compressed into very specific time windows. And safety is about ensuring that these things can happen in that domain. So why is this challenging for Linux? We have real-time for Linux, but that's not quite what safety is about. Linux itself kind of has some problems. It is not designed to be a safety environment. It is designed kind of primarily for performance and for other various reasons. The development process itself, I mean, I can't think of any reviewers right now who review patches with safety criteria in mind. So it's not kind of baked into the development cycle right now. The design of Linux, it is, again, built for performance, but it's a monolithic kernel, which is great for doing things quickly, but that doesn't come with isolation. It doesn't come with different levels of privilege. And quite frankly, it makes it easy to, one bug in one area to cause a problem in another. And that's a big problem here. Linux, as all of you know, is very large and moves very fast. I'm referring to the Linux kernel, of course. Millions of lines of code, even if you configure it down to a much smaller subsystem, you're still in the millions of lines of code domain. And you get 9 patches, the maintainers get 9 patches per hour that integrate into Linux. That scares a lot of people in the safety domain because they want very fixed configurations, and this is a large moving system. How do you qualify your code? There's an interesting complexity angle to it. So when you've got very simple functions, stateless, single input, single output kind of functions, it's very easy to test those and say, all right, based on all the known input parameters, we know the behavior, we're getting the correct output parameters. But as the complexity scales up, it's very hard to qualify that for correct behavior. Once you start getting into stateful functions, multiple inputs, multiple outputs, you can still kind of do that effort-wise. But once you start building larger groupings of these things into subsystems, they're interconnected, multiple different states to convey, your qualification accuracy, your ability to correctly make claims about the behavior of those systems goes way, way down, and your effort goes way, way up. That's another challenge with Linux, especially since the valuable areas of Linux are the most complex. Schedulers, memory managers. Anybody who wants to qualify the networking stack kind of runs away screaming. It's kind of complex. All right, bit of an eye chart on this one, but what it's basically saying is there's a scaling problem with Linux. You can do some of these things at the function level, and there's many actual decent ways to qualify a function. You can do traditional safety methods, which is kind of what's called the V model, essentially a waterfall design with parallel verification and traceability built into it. You could do something even fancier like formal methods. I've seen people try to claim proven in use, but no safety managers really like falling back in those arguments. You can do other things like put in monitors in the system or build up redundant pipelines. There's a lot of ways to work around it. But you have to be able to scale these out to an entire system. And in Linux, it has some challenges with that. So the approaches that we've generally seen people take, reduce the problem size. And in theory, you can keep doing that, but you start throwing away the things that make Linux valuable. Chunk out your debug subsystems, your tracing subsystems, because they're not safety relevant, but then your system becomes very hard to use. Or you recognize that this complexity is too much to deal with and you treat it as a black box and you look at it from the outside, which you can do some monitoring, but then you're subject to latency concerns. So your ability to detect issues in a timely manner becomes challenging, especially as you get up to higher and higher safety levels. So scaling this across Linux is a challenge. Your mileage may vary in this one, but just to put some additional context around it, much older project, we estimated that coding, testing, plus all the safety rigor around it, we were able to get through about 1,500 lines of code per engineer. If you scale that out to something the size of a minimally configured Linux kernel, 1.8 million lines of code, gives you about 1,200 engineering years of effort to do a safety qualification for the entire Linux kernel itself. And you can plug in your own cost to that, but it easily starts getting up into the hundreds of millions of dollars to go through a safety certification using those kind of traditional methods. It doesn't scale very well, and it's not very repeatable, at least in our opinion. All right, so yes, of course, we have our own ideas about how to approach this, and they're going to address some of these problems. So after thinking through this a while, we realized there was one fundamental piece missing, and that was a proper solution to spatial interference. Spatial interference is safety terminology. Interference, something that prevents you from achieving your safety goal, which is another way of saying a bug. Spatial interference just means something not happening in the place where it should. So data corruption, for example, buffer overflows, those are all spatial interferences in a safety context. This particular example, you've got processes in user space not safety related, NSR, processes in user space that do have safety requirements, safety related processes, and additional safety related requirements being mapped in the kernel itself. And then you have all these nice, wonderful bugs walking around in this monolithic kernel who can now interfere with anything else running in the kernel, and they can interfere with user space behavior. From a safety perspective, that's a little bit problematic. You don't want your image recognition, your actuation functions to not run when they should or to have corrupted data. So that's the fundamental problem. How do we prevent all these bugs from interfering with our safety goals in the Linux kernel, and without rewriting the kernel itself and changing the entire development process around it? So our proposal to this solution is drawing a box around our safety relevant code, and we're treating this as a safety specific context. And what this means is essentially different memory maps for safety relevant code. And the context is then shared between user space and kernel itself. It's a little different way for the kernel to operate, but once you have a different memory context, you are swapping out your page tables as you're executing through kernel, switching between these contexts. These pre-existing bugs, which in previously you needed to put a lot of effort to find and stamp out and get rid of, and that never really happens because we've got LTS kernels and they all have bugs in them. But these bugs now can be provably shown to not interfere with your safety context anymore. And that becomes a powerful mechanism for giving proof that your safety goals can be met in the system. So there are a bunch of different safety integrity levels. This chart just kind of shows that when we're building a memory context, we are, by our choice, making them directional. So as Diego mentioned, there's a bunch of different safety integrity levels. QM is quality managed. It's kind of the lowest level in automotive safety. ASIL B goes all the way up to the kind of robotaxi domain. And in reality, we only really see QM or B or D. I've never seen a system with A or C in it anywhere. But at least in our scheme, we're introducing some directionality and writes between these contexts. Your current context can read and write, and anything can read anywhere, but your current context can write your equivalent safety level or lower because you trust that code, you vetted it, it can have broader access. Your highest safety context code, ASIL D, can write anywhere it wants. You put the most rigor into that, you trust it. Your lowest level code, which can be from anything, you don't have to put as much rigor into that because it's write prevented from accessing anything else you put into the safety context. So to do this, it actually takes some changes in the system. We actually have to add a safety dimension to memory allocation. That's kind of a non-trivial thing. And because we have essentially different page tables, different memory maps for these contexts, as we're executing throughout the kernel, we have to know when to switch between them. So that implies some kind of intelligent application of context switching within the kernel. You want to do it as little as possible, as much as necessary to achieve your goals. This comes with some performance costs, as is typical in safety and security kind of things. But for us, it's a little bit increased memory utilization from additional memory being present in the system or reserved, and increased CPU utilization depending on how you use this. But it also gives you a knob for fine-tuning your system. If you're willing to put in more work to safety qualify your code, you can broaden your context windows and do less context switching in that case. So it then becomes configurable based on how you want to use it, which is another interesting kind of knob in the system here. To give you an example of what that looks like, on the left is a kind of typical memory allocation. You're executing code somewhere, you allocate it, typically comes out of a page cache, which is replenished by a memory pool eventually. In a safety system, the same exact thing appears there, but now you have to dimension your page cache, you have to dimension your system memory pools. And then you have to be able to allocate from the correct context. So there's some context awareness that comes into your memory allocation. You have to know when you're in this elevated context so that you can get memory of the associated integrity level back with it. And then, of course, the memory pool has to backfill appropriately. And here's where safety kind of comes in. You now have a safety requirement to allocate the proper memory per your context. So you put in a validation monitor, basically make sure that the page you get back comes from the right place, and then that's where you do your safety. This is a powerful way to apply it, in my opinion, because we do not have to safety certify the memory allocators themselves. We can let them do their job uninterrupted. We just have to verify that they do the correct thing when they return a page to us. Context switching, I mentioned. This is a contrived, kind of simple example, but you can imagine you've got a device driver that is in a safety context. A very common thing for a device driver to do is make print statements. We do not want to safety qualify print K. I've read the code. I don't want to make safety arguments about it. It's very fine code, but it's not amenable to easy safety certification. So you can imagine in this case, we're going to do a context switch. We're going to execute print K. We know in that case we're not susceptible to buffer overflows because now they would trigger an MMU exception. So we can do that with some verifiable claims about our safety and come back. The trick in this comes with nested functions that also may need to write to a safety elevated context. A simple example, you allocate a page, but then you need to clear the memory itself. So now you have to have some awareness in your call chain where these additional writes might need to happen. So you do need to be able to analyze your system, understand where down the chain you might need a context switch later and give some awareness to that. You need to find these points. So in this case, you allocate a piece of memory, you downshift, run the memory allocator. All right, we need to write to it. We upshift back to our safety context, do the write, it's done properly. And then we have to unwind all that to get back to our driver and continue our normal execution. But you can imagine this gets a little kind of complicated and you need to do a lot more analysis about where these contexts might apply. Package this all together and there's some fundamental changes to the system. For us at least, we are kind of pre-allocating memory because that's our own particular safety requirement for it. So as part of kernel initialization, as part of user space initialization, we are doing safety-related functions first, device driver initialization, memory pool allocation. So there's some ordering things we have to work through there. And then after we get done with initialization, we actually lock down those mechanisms. We actually have a requirement that says, all right, we're not going to allocate any more safety critical memory at this point. So anybody else that tries to do that will run into exception. It's not an allowed behavior in our system. But this gives us at runtime something that's a pretty normal system if you're not in safety relevant code. The rest of the system doesn't even know about this. It can run untouched, unaware, run like normal. We have passive mechanisms in this case, those MMU boundaries where if something misbehaves, it'll trigger that and we'll know. And then we can take some remediation based on the severity of the violation there. But this also gives us the ability to put in active testing mechanisms. We can actually go through and periodically verify that, oh, by the way, these triggers are working properly. We can trigger these things and make sure that the runtime mechanisms are still in place. So there are some very actionable methods that we can use that give a lot of comfort to our safety managers that these mechanisms will be safe for deployment. Zooming back out to another level, a lot of these changes, because of the way they deal with memory, they're highly intrusive into the Linux kernel. And because memory is translated up into user space layer as well, we have to have some knowledge about these systems up into some of the init processes in system libraries as well. And that's kind of the extent of the changes that we anticipate. If you have your own safety related applications, of course, they have to be in a context here. But if you don't, there's no more awareness, and nothing has to be aware of this at all. One of my favorite things about this approach, it is based on existing safety standards. It does not require the safety community to adhere to any particular new methods or terminology or anything else with Linux. The safety folks understand how this behaves because it adheres to existing standards, and it does not require Linux to fundamentally change kind of process-wise. We can distill it down to kind of necessary kind of code changes, and then safety rigor can be handled by those who really need it. At the end of the day, we are left with what we believe is a very robust solution to spatial FFI, spatial freedom from interference. All the unknown bugs we can demonstrate cannot affect our safety-related goals, or at least we can detect them and work around them. So we have monitoring capabilities around this, and every safety system usually also has temporal FFI solutions as well. There's a lot of solutions in there, watchdogs, other kind of monitors. They are part of our solution as well, but they're not any kind of new development here, so I didn't go over those in depth. And again, the new thing here, we are not building an entire safety system. We're not claiming that everything is safe. We're claiming that where safety requirements apply to a system, we can isolate those, and we can protect those, and then we can make claims about their behavior, verifiable claims as well. So that's really kind of the new big thing for us. As fond as we are of this ourselves, at least in the automotive domain, the common practice is to take your products out for third-party assessment. So this is not yet a product, but this is a concept for us. And so we took it out to one of our third-party assessors, to SUD. We reviewed the concept, that behavior with them, and they agreed with our assertions that these behaviors, as described, will meet ASIL B expectations against the existing standards for automotive safety. And that gives us a lot of confidence that this solution will be deployed and will be accepted by the safety industry itself. So we're very confident in this approach right now.